Well, there's a lot of information in a right triangle. For a triangle, we could have the facts about the lengths of the sides and the size of the acute angles. Solving a right triangle means we're going to find all the missing parts. So here's a picture of a generic looking right triangle. What makes it a right triangle is that this angle is a 90-degree angle, and opposite it is the longest side of the triangle. That's the hypotenuse. Hypotenuse C, by standard labeling, opposite the 90-degree angle. Now we'll have an acute angle alpha, and alpha is opposite one of the legs of the triangle. That by convention will be alpha opposite A. And the other acute angle, the angle that's complementary to alpha, is beta, and beta is opposite B. So we're going to solve the right triangle by taking information that's given about some pieces here, sides or angles, and if there's enough information given, we can find all the missing information, and that's what solving the triangle is. For example, here's a triangle labeled where an angle and an angle. This is beta, this is alpha, so this is A. Beta is opposite side B, and the hypotenuse C. I'll specify a length of A being 4 and angle alpha being 35 degrees. To solve the right triangle means we're going to figure out what B is, side B, hypotenuse C, and the other acute angle, beta. So let's go at that. Maybe a first way to use information that's given to get other information: angle, side opposite. Say we'll go for the hypotenuse. If we know about an angle, sine of the angle is opposite over hypotenuse. So sine of 35 degrees is 4 over C. That's great. That's an equation that has only one unknown value, C, and we can solve for C. C would be 4 divided by sine of 35 degrees, and that would be value 6.97. Let me pull up the calculator and do that. I'm going for the Windows calculator. It's set up in the right mode for scientific work, so I've got the trig functions built in. So let's do 4 divided by, this is in degrees and it's in degree mode, so 35 degrees, and we want sine of 35 degrees. 4 divided by sine of 35 degrees equals, and there's this 6.97 that shows up. Let's get the next piece that's missing. Now we know one side C. Let's figure out what B is. Again, we can work from given information, angle, side opposite. If this time I'm interested in side adjacent, I can get that by thinking about the tangent function. Tangent 35 degrees is opposite over adjacent, 4 over B. That means B would be 4 divided by tangent 35 degrees, and there is a numerical value, 5.71. This is worth checking just to notice that something is consistent, that C, the hypotenuse of the triangle, ought to be the longest side, and the value that we calculated for C is longer than the value that we calculated for B. So that's a good thing. At least we haven't made a really silly mistake. The only thing that's missing is beta, and that's easy because alpha and beta are the missing angles in this right triangle. 90 degrees for the right angle, so it's 90 degrees between them. These are complementary angles, so beta is 90 minus 35 degrees, and there is a numerical value for beta. So we've solved the triangle. We found all the missing pieces from what was given. Let's do a problem with right triangles that looks a little bit more anchored in the world. Here is a situation, a ladder leaning up against the wall, a length of the ladder, and an angle that the ladder forms with the ground. And we can figure out how high up on the wall the ladder is by treating that as a side of a triangle. Let's draw a picture in to make a triangle, 25 feet for the ladder, 70 degrees for the angle, and how high that reaches up the wall is what's asked for. That's clearly the side opposite this 70-degree angle. So we can answer the question by applying right triangle trigonometry. Sine of 70 degrees is opposite over hypotenuse, h over 25. So h, when you solve that by multiplying both sides by 25, h is 25 sine 70, and a numerical value 23.5 feet. Here's the calculator to do that. Let's clear out the last calculation, and I'd like 25, that's that number, times degrees, it's set in degrees, 70 degrees has a numerical value for sine of that number, and when I multiply that by the 25 that was in there, that's the 23.49, rounded to 23.5. Here's a more involved problem. This one's set up involving a nursery. Yola plants a tree. The tree grows at a certain rate, says the nursery, and Yola wants to see if that's so. So she is going to figure out the height of the tree and the height of the tree a year later and see if it's enough to be the growth that the nursery claimed. Let's see if it is. She's going to march 100 feet from the base of the tree and measure what the angle is. So let's try to draw a picture to capture this information. We've got I want the picture. I don't want to look at this yet. Let me go to the picture. This is what I want to think about. 100 feet as the base of the distance out from where the tree starts. 2 feet up from the ground for the height of the transit. H for how high that tree is after 2 years, and G as the extra growth, so G plus H is the growth during the first year. We'll make 5.7 degrees as the given angle for the first year relative to this side H, and 11.9 for G plus H. So tangent of 5.7 in this little triangle, opposite over adjacent is h over 100. And in the larger triangle with the angle 11.9, it's g plus h plus g for the side opposite, and still 100 for the side adjacent. Sorry about that. I had my slides kind of out of order, didn't I? So the h value that we calculate, since tangent 5.7 was h over 100, h is 100 times tangent 5.7, so 9.98. We'll do it for the angle 11.9, h plus g over 100, and we find h plus g is a numerical value 100 times the tangent of 11.9. So out comes a value from the calculated value of h that we had. We can get the value for g as built on that h. And that means the g value is 11.09 as the difference between 100 tan 11.9 degrees and the calculated value for 100 tan 5.7 degrees. So this 11.9 is an interesting number. That means the tree grew after a year to a height that was 2 for the height of the transit, 9.98, the value of H was the growth during when the tree was first planted, and 11.09 for the growth during that year. So that's not enough to support the nursery's claim that the tree grew it at a rate of 12 feet a year. A little bit short. Viola, I guess, has to decide if that's enough to get her money back, or if she's going to keep that tree she's grown attached to it, maybe. Okay, that's right triangles. And there's some other supplementary presentations. There's one about Woodburn Hall that you might find fun to see. Look at some of the other units in this section.